Hello and welcome to the fourth installment in our LPDA Grand Tour of SuperNEC. Today we're going to be exploring the output interface. In our previous video we actually went into great detail regarding the simulation settings we've set up. If you haven't seen those, please have a look. For now I can just quickly show you what we set up before we started. You'll see here I have a summary of all the things we've changed with regards to customizing our simulation settings. I've added some radiation patterns, I've added a near field. Once again, don't work too much with the interaction range and the UTD. This is my frequency range, this is the kernel. Please feel free to look through the simulation settings video, otherwise this might get a little confusing. And now for the matter at hand. Press the simulate button. Always save the changes to your output file, as SuperNEC will create an output file. There we go. The command window is basically just going to be showing you that the program is running and at which frequency increments it's currently simulating your project. Alright, once the command window is shut down and we've simulated everything, you now have an output interface in front of you. The output interface has 4 sets of menus here at the top: radiation pattern, near field, currents and charges, and parameter versus frequency. In general, they have a couple of things in common. You'll see there's a filter available structures box over here, there's a filter available frequency box over here. So when SuperNEC actually writes an output file based on this output interface, it's going to be doing it selectively. So what I'm trying to say here is if you don't add it in these set of boxes or in the small specialized box for each of the different types of menus, it's not going to be passed through to your output file. Just keep that in mind. For example, if you have multiple structures here, or if you want only specific frequencies, you're going to have to select them in these 2 boxes. Starting on the far right, parameter versus frequency, basically this is going to be everything with regards to any parameter versus the frequency change you've specified. There's the efficiency of the model. Given that we've added no lossy elements to our design, it's going to be 100% efficient all the time. Likewise, because we haven't introduced any elements to affect it, the axial ratio for this specific simulation will be set at 0 all the time. And here I have the gains model. I'm going to plot that for you. And here we have the overview of our gain versus the frequencies we've simulated at. It looks a little choppy here, but if you just actually decrease the increments at which you're simulating, you should get a nicer version of it. We can also show a smoother version of this gain graph. If we go up here, go to access limits, select manual, and if we can just change this Ymin and Ymax from -10 to 10, it should give us a better shape of the gain overall. And you'll see that's slightly smoother and a bit more what we expect. As I mentioned, and I will reiterate, you can also just change the increments at which you're simulating at to a lower frequency. So what we're doing is we're doing 5 MHz at the moment. You can decrease it down to 1. Just keep in mind that it'll take longer for your simulation to run. And in terms of everything else, there's not much that I haven't touched on here. You can edit the title obviously here, you can edit your legend here. And that's all I'm going to be touching with regards to the gain plotter. Moving on to the excitation. Press plot again, keeping in mind that this is all frequencies. And here we have a Smith chart representation of the excitation on our model. And remember when I was actually using the how-to videos where I was explaining the impedance plotter and the coupling plotter and everything to you, that they all work on the same principle? This one is working with the impedance plotter. You can see here at which frequencies we're actually close to match point and where we break out and spiral out in this direction. In terms of the Smith charts, we can go impedance, admittance, which is obviously just going to be flipped. You can also work in terms of the impedance, admittance and reflection coefficient on magnitude. This is going to be magnitude versus frequency. Phase, once again, in all these menus you will have the 3 options: impedance, admittance and reflected coefficient. You can get your real and your imaginary factors. And here is the VSWR, which is pretty typical in an LPDA. And lastly, you can also check your return loss. Once again, we have all these things that we can adjust, the axis limits, axis scaling, and the ticks. Not really necessary to go too in depth with that. Now we're back into our main output interface with the parameter versus frequency menu. As we move on to currents and charges, I'd actually like to draw your attention to these two little tick boxes down here in the bottom left, labeled structure and overlay. Structure is when you want to superimpose your structure onto your graph, and overlay is basically where you can add multiple graphs on the same set of axes. The reason structure is automatically filled in here and you don't have the option for overlay is that our current and charge distribution is actually going to be shown on our segments, so it's already present and we don't need to specify it. The first thing I'm going to do here is I'm going to be selecting all frequencies. I will once again press plot. And here you can actually see the current distribution as it goes through our LPDA. We have a frequency slider that's present here at the bottom. And the nice thing about the current and charge distribution is that you can actually vary your frequency and see how the current is going to be changing according to the basis of an LPDA. The scale here should give you a pretty good idea of where your current is most concentrated in your segments. And you can see it move down the LPDA as we increase our frequency, and eventually our design will break down. While we're here on the currents and charges menu, I'd like to draw your attention to this little button over here that says load. Load actually allows you to directly feed data from your SuperNEC simulation into your MATLAB workspace. So basically what will happen if you press load is you will be prompted to provide a variable name. If you have selected only one set of data, for example you only want your electric near fields, it will appear in your MATLAB workspace as a normal sort of data set. But for example, if you selected multiple sets of data, for example your electric and magnetic near fields, you're going to have to once again name it, and it will be set as an actual structure or struct in your MATLAB code, and you'll have to access the elements as they were named individually in your MATLAB code. The next menu we'll be exploring is the near fields menu. Select all frequencies. Here are the specifications I've actually set up for our near field as per the simulation settings video. If you'd like to have a look at that, please go back and see, but that's where this set of information comes from. And the first thing you'll notice is that, as I mentioned in the simulation settings, there's a couple of things with regards to near fields that we'll be working with. In our near fields we could select stuff like the major, minor, electric or magnetic, and we could select the planes in which we're going to be simulating our near fields. I've shown you how to set up the X, Y, and Z planes you'd like to work with. I've shown you that you can select an electric field, you can select the shape of an electric field, for example spherical, cylindrical, or rectangular. Likewise with magnetic fields, and I've said it before as a little disclaimer in the simulation settings video. We cannot actually get the near field viewer to differentiate between the electric and the magnetic near fields. And we also cannot get it to differentiate between the major vertical and the minor horizontal. For this reason, it's not really wise to go control all on these, so select a specific frequency at which you would like to see your near field. I will go with 160 MHz. Once again, press plot. And here we have a representation of our near field and a slider down here for our Z plane. Recall that I set up a Z plane going from 0 to 0.5. So you'll see as I increment this, my max will be 0.5. And basically I'm just moving through my near field per the planes I set up in the simulation settings. Once again, Y I set up from, I believe it was minus 0.5 to 0.5. There we go, as I go through that. And lastly, X was also set up to go from minus 0.5 to 0.5. And there you see we're moving through the X plane. Just going to reset it to Z. Here you have a couple of options of the view you can work with. We have it set to magnitude, which is pretty normal. You can view the X component, Y component, and Z component. These are pretty self-explanatory. You have the wireframe, mesh, and surface, contour 3D. These are the ones that are actually going to be using your Z-axis to create an impression of your gain in different directions. So you'll see here I have a p-color plot representation of our near field. Both the p-color and the contour plots are actually sort of topographical representations of your gains. Basically what that means is if you had to picture a map and the different colors were greater intensities of gains, then that would be what the p-color plot does for you, or the pseudo-color plot. Here you can change some of the more pedantic details. If you're doing this for a project, for example, you can add the grid, you can change your title, X label, Y label, stuff like that. MATLAB is hugely versatile in terms of its visual library. Color map, likewise. And tools basically is going to be the to workspace button, which I explained to you is sort of like the load button over here. And that's pretty much it for the near field viewer. Last but certainly not least, we're working with the radiation patterns. Recall from the simulation settings video that I actually added 2 sets of radiation patterns to my simulation. I added a 2D plot and I added a 3D plot with a 4-degree increment. Press Ctrl Alt. While I'm actually working with the radiation patterns, since they actually work quite well for this, I'm just going to show you how the structure works as well. Press plot there, you'll see we have a 3D radiation pattern and a 2D radiation pattern. As I go through my frequency ranges, you'll see the 2D radiation pattern change. But what I'm more interested in is the 3D radiation pattern. I'm going to actually make this full screen just so that we can see. Zoom that in. So this is at our lowest frequency of 100 MHz. This is our 3D radiation pattern. And you can see, because I ticked the structure box, here is my LPDA. We once again have a very convenient frequency slider available to us. The frequency slider, however, will always jump to the nearest available point of data, and it's often based on what sort of increment you set up in your simulation settings. We did 5 MHz, so there we go. You can see it sort of balloon out and change as it moves through the structure at different frequencies. Another thing you'll see in line with this frequency slider is we have a tick box, drop down menu, edit window, we have another slider, and we have a 2D button. The first thing you're going to want to do is you're going to need to press that tick box and you'll see everything becomes nice and grayed in, meaning we can make a selection. Recall from the simulation settings video that we worked with phi and theta in both cases. Phi and theta were present when we were selecting our specific radiation patterns, and this is where we're actually going to be having a look at them more in detail. I told you in that specific video that phi is basically going to be a longitudinal cut. So as a compass would move on the Earth, it's going from 0 to 360 degrees, and once it passes 360, it's going to be going back into the range of 0. So you basically slice it straight down the middle like that. I'm going to go through it. There we go. You can see how that line moves through and returns to 360. Change the selection to theta. For this part, I'm just going to rotate for us again. Okay. Now theta is basically going to be latitudinal cuts. So 180 is going to be right here at the bottom, and as I decrease it, you'll see the line move through my 3D radiation pattern. And if I press 2D, I will have a lovely 2D representation of the radiation at the specific point in theta that I actually wanted to see. Another nifty thing that you can actually do with the 3D radiation pattern viewer is here. If you go onto view and you select exclude, you can now set a range in which you'd like to actually take a quote-unquote slice out of your 3D radiation pattern. So do it as per the recommended format over there. Set up a range in phi and set up a range in theta. Okay. So here you can see I've taken a lovely slice out in the range of 180 and 90 degrees. In terms of the output interface, I think that might be everything we're going to be covering in this specific video. Please do let us know if there's anything else you'd actually like us to explore in this series or in a future series. There's possibly another video on the LPDA Grand Tour, but for now I'm just going to say thanks so much for watching. Drop a like, subscribe. We'd really love to get your opinion in the comments down below. Have a great day.